Wire antennas, elementary dipole series on antennas and wave propagation, lecture number 2.11. Study of elementary dipoles have a lot of significance and importance in antenna theory. Elementary dipoles, they are capable of providing a key to have a deeper level of understanding in the functioning of not only wire antennas but other types of antennas too. In the present session, we focus on finding the fields in the wave emitted by an elementary dipole along with its performance indicators like radiation resistance, directivity, effective length, etc. Let us begin the session with an introduction cum definition of elementary dipoles. It is an infinitesimal length dl less than or equal to lambda by 10 of a wire carrying in phase current I cos omega t. This is definition. It carries in phase current. Length should be small, smaller than lambda by 10. Lambda is wavelength. These two are critical points one should keep in mind while giving a definition to elementary dipole. It has several names. One name is short dipole with a uniform current distribution. Another short dipole is also there, but it carries linear current distribution. Elementary dipole carries uniform current distribution. Of course, it is usually called elementary dipole. Another name is hedge dipole. Still another name, AC element. AC stands for alternating current. It is also called differential current element. Conceptually, this radiator is considered as a building block of a physical antenna. So functioning of a physical antenna can be understood by considering it as consisting of several elementary dipoles. Once we have a thorough understanding regarding elementary dipole, applying superposition principle, we can have an understanding regarding the actual antenna. Some more points regarding this radiator. It is not a practical antenna. You cannot find it in reality, but have tremendous theoretical significance. Its analysis is able to give deep insights into the functioning of radiators. It can be considered as a small length of transmission line conductor carrying standing waves. This is transmission line. Let us say it is open circuited lossless line. As it is open circuit, load is open circuit, entire wave gets reflected. Therefore, a standing wave pattern comes into being over the line, over the conductor. Consider small length of one conductor, the small length with its current distribution. When length is small, notice as it is the current distribution is varying somewhat sinusoidal manner, similar to sinusoidal variation. But if you consider small length, then the variation in current can be neglected and it can be assumed that current variation is nil or current is uniform. This is a small length conductor. It is our elementary dipole. It is a resonant radiator and its analysis can be extended to understand the nature of other resonant radiators. Amplitude of current is assumed uniform all along its length. Analysis is determining fields around with the help of Maxwell's equations via vector potential from the given current distribution. Analysis can be done in time domain as well as in phasor domain, but in the present session we did it in time domain. This particular slide gives plenty of information, useful information regarding the nature of elementary dipoles. Here is shown an elementary dipole located in a spherical coordinate system. Here it requires to be mentioned that it is the spherical coordinate system that is widely used in antenna theory. It has its own advantages when used in antenna theory. X-axis, y-axis, z-axis. Theta is polar angle, r is radial vector. Phi can also be defined, azimuth angle. Here is a point P. It is called field point. It is supposed to be at a large distance from the dipole. R should be large. Length of the dipole is dl, differential length, small length. It is placed along z-axis with its center lying over the horizon. Field point is making an angle theta to the z-axis. So we use this geometry in the analysis. As already mentioned, the purpose of analysis is to find field components. Elementary dipole, it is carrying a certain current. This current radiates. It gives out electromagnetic wave. This wave is associated with fields, electric field, magnetic field. The purpose of analysis is to find electric field, magnetic field, and some other quantities too. At a point, arbitrary point P. This point is called field point. In the analysis, what is done is from the current distribution over the dipole, vector potential is calculated. From vector potential, magnetic field intensity. From magnetic field intensity, electric field intensity. From electric field intensity, power and other quantities of interest are calculated. In B, in this diagram is shown resolution of A, vector potential, which is entirely in z direction, Az, into two components, radial component and theta component. The current in the elementary dipole is in z direction. It gives rise to magnetic potential in z direction because potential's direction is the same as current direction. So at point P, potential is in z direction. So Az is due to dipole. In B is shown resolution of Az into two components, Ar and A theta. Now let us move further into the analysis. The fields around this radiator can be found using the following sequence of steps. It starts with current, then to vector potential, to magnetic field, and finally electric field. Magnetic potential A of RT by definition is mu by 4 pi integral J of T minus R by C over R d tau prime. This is basic definition, fundamental definition of potential, vector potential, but it is in terms of volume currents. D tau prime is volume element, differential volume, but there is an identity, equality. J d tau prime is IDL. We can use this identity and write down A in terms of ordinary current, linear current. When we adopt that relation to the present situation, we get AZ. AZ means Z component of A. A is a vector. Here, Z component of AZ in the present case is mu by 4 pi. I, we know, is I cos omega t, but in place of t, we have to place retarded time. Then we will be getting mu by 4 pi Im dl cos omega t minus r over c by r. This is AZ. AZ can be resolved into two components, r component and theta component. In the previous slide, it is shown AR is AZ cos theta, A theta is minus AZ sin theta. A phi is naturally 0. The reason for resolving AZ into r theta phi components is we want to do the analysis in a spherical coordinate system. So we need to convert A into r theta phi components. And now A is related to H. Mu H is del cross A. This is basic relation, fundamental relation from electromagnetic field theory. Mu H. H is vector, so it has three components: theta component, r component, phi component. Substituting theta component, r component, phi component of A in del cross A and computing del cross A, we will be getting three components. Del cross A has three components because it is a vector. Equating these components of del cross A with the components of H, we will be getting three equations. Those equations are given here. Mu H theta is del cross A theta. After computation, one can find it is equal to 0. Mu HR can be found equal to 0. It is del cross A R. Del cross A R can be found 0 after substituting A R A theta A phi in del cross A. So we are left with only one component, phi component. Mu H phi, it can be found as 1 by R dou R A theta by dou R minus dou A R by dou theta. A little bit of manipulation gives it equal to 1 by R A theta plus R dou A theta by dou R minus dou A R by dou theta. Ultimately, one can show it, see it equal to minus sin theta dou AZ by dou R. AZ is already available. So substituting AZ expression in this equation and doing a little bit of manipulation, we can have H phi as Im dl sin theta by 4 pi minus omega sin omega t prime by rc plus cos omega t prime by r square. T prime means t minus r by c, retarded time. So H is now available. HR, H theta are zeros. H phi is now computed, available. So H is available. From H, one can find E using this expression. Del cross H equal to dou E by dou T epsilon. This is the Ampere's law. Using this expression, one can determine E. After doing integration and manipulation, we get E theta as Im dl sin theta by 4 pi epsilon into minus omega sin omega t prime by rc square plus cos omega t prime by r square c plus sin omega t prime by omega r cube. ER can be found equal to 2 Im dl cos theta by 4 pi epsilon multiplied by cos omega t prime by r square c plus sin omega t prime by omega r cube. H phi equal to Im dl sin theta by 4 pi into minus omega sin omega t prime by rc plus cos omega t prime by r square. Here notice in the expressions of these fields, certain components are varying inversely with r cube, some are varying inversely with r square, some are varying inversely with r in E theta. In ER also, one part is varying inversely as r square, another part is varying inversely as r cube. In H5 only inverse r component, inverse r square component parts are there. So this is an important observation. Variation with inverse r, variation with inverse r square, variation with inverse r cube. These three variations are there in the fields. Now, the average power radiated by the element is given by radial Poynting vector. P is E cross H, we all know. If E and H are amplitudes, then half will appear here. Average means you have to consider small integration, averaging over T also. So 1 by T, 2 if these are amplitudes. Otherwise, 2 need not be there. Right, now P or average. P is a vector. It has three components: radial component, theta component, polar component, and azimuthal component. See, this is a dipole. Radial component means power flowing away. This is a radial component. Polar component means power that is rotating around the dipole in a vertical plane. That is theta component. Phi component or azimuthal component is one which is rotating in a horizontal plane. So theta component, phi component, they are powers that rotate around the dipole, whereas radial component represents the power that is moving away to far away places. Here we are considering a radial part, the power that is moving away. It can be shown equal to 1 by T integral T E theta H phi dt prime. E theta is available, H phi is available. Substitution and a little bit of manipulation gives us eta by 2 omega Im dl sin theta by 4 pi rc whole square watts per meter square. Here eta is intrinsic impedance of the medium in which the radiator is located. If it is a free space, then it is 120 pi or 377 ohms. So some power flow is there. Here is radiator. When you drive current into this radiator, and when this current is time varying, then certain power flows out into space, and this power is called radiation. Some power also exists which will be rotating around the dipole, but that power is not much benefit or significance. Of course, it has certain nuisance value. We discuss about it soon. Now, radiation term amplitudes. In the previous slide, we have computed power that is flowing away from the radiator, and it is mentioned there that this power is called radiation. Name is given to this power, it is radiation. And this radiation is contributed by two field components. One is E theta, theta component of E, and phi component of H. Other components, R component of E or phi component of E, they do not contribute to radiation. So theta component has certain significance, importance. So what is the amplitude of E theta? It is Im dl sin theta by 4 pi epsilon omega by rc square. We have expression for E theta earlier in a previous slide. There we can see three components or three parts. Three parts. One part having inverse R relation, another part having inverse R square relation, last part having inverse R cube relation. R square relation term, R cube relation term, they don't contribute to radiation. So two aspects one has to keep in mind. ER, E5 do not contribute to radiation. This is one aspect. Second aspect, in E theta 2, term carrying inverse R square and term carrying inverse R cube, those two terms also do not contribute to radiation. Only inverse distance term of E theta is the one that contributes to radiation. So its amplitude is given by this. A little bit of manipulation ultimately leads to E theta as Im dl sine theta by 2 lambda r square root of mu by epsilon. Root mu by epsilon is eta, intrinsic impedance. It is usually indicated by eta. Intrinsic impedance is indicated by eta. Ultimately, it comes out E theta amplitude comes out to be 60 pi Im dl sine theta by lambda r. This is the relation we are going to use. We use frequently, so better have it in our minds. Similarly, H5. H5 also has two terms. Inverse R term, inverse R square term. As already mentioned, inverse R square term, inverse R cube term, they don't contribute to radiation. So we are not interested in those terms while analyzing radiation, while studying, while our interest is in radiation. H5 amplitude can be shown as of Im dl sine theta by lambda r. Notice E theta by H5, that ratio can be computed. E theta by H5, it turns out to be eta, 125. Now from the expressions of the fields, one can make certain observations. These are a lot of significant ones. So better follow them seriously. First observation. Fields around the radiators can be divided into three categories on the basis of their variation with the distance. Fields with inverse distance variation, that is 1 over r variation, they are called radiation or acceleration or far fields. Fields with inverse distance square variation, 1 over r square variation, they are termed as induction fields. Fields with the inverse distance cube variation, 1 over r cube variation, they are called electrostatic fields. 1 by r cube fields or electrostatic fields, they are dominating near the radiator. If you move slightly away from the radiator, as r becomes large, their amplitude becomes insignificant. So slightly away, 1 by r cube fields become insignificant. So 1 by r cube or electrostatic fields dominate. They are influential near the radiator. Slightly away means they are dead. Fields with inverse distance variation, they dominate at faraway points because variation is inverse distance variation. It is not inverse distance square, it is not inverse distance cube. Therefore, dependence on distance is not that much as in case of distance square or distance cube fields. So radiation fields, 1 by r fields, are dominant at faraway points from the radiator. In between, induction fields dominate for some distance. So near the radiator, it is electrostatic fields. Far away, it is radiation. In between, induction fields. Observation 2. The electrostatic and induction fields are predominant in the regions near to the radiator. only at small values of R, and radiation fields are dominant for large values of R in the regions far away from the radiator. 3. The near field term is only of electrostatic field, and there is no magnetic field term with 1 by R cube variation. Also note that near field is far more complex than radiation or far field. Observation 4. When the time variations of the source current are cosinusoidal, the time variations of the radiation fields are sinusoidal. Hence, radiation fields of the electric dipole are in time phase quadrature with current over the dipole. This is an important observation. Fields are in time quadrature with currents over the radiator. Another observation, fifth one, the magnitude of the electrostatic field is inversely proportional to frequency omega. The induction field is independent of omega, and lastly, the radiation field is directly proportional to omega. This is an important observation. Magnitude of electrostatic field is inversely proportional to frequency. So, frequency more means electrostatic field becomes less. Induction field is independent of frequency. So, induction field doesn't vary with frequency. Radiation field is proportional to omega, means if we want more radiation from the radiator, frequency should be high. Another observation 6. At low frequencies, as magnitude of 1 by R cube field electrostatic field is large, the fields are more localized around the source, whereas at high frequencies 1 by R field radiation field is dominant, and hence the field can reach out far away distances from the source. This is the reason for more interference at high frequencies. It is mentioned already in a previous slide that near to the radiator, electrostatic fields are dominant. Far away places, it is radiation fields that dominate. That is one aspect. Another aspect is at low frequencies, 1 by R cube fields are large, means electrostatic fields are large. At low frequencies, these fields which are near to the radiator, they dominate, they become large. But at high frequencies, radiation fields, they become large, they are large, they dominate. 7. Domination may not be the right word, but here right word is, with frequency, radiation fields become large. Another observation, all the three fields become equal in magnitude at a distance of approximately lambda by 6 from the source. Distance lambda by 6 is called radiant distance. The sphere with the radius lambda by 6 surrounding the antenna is called radiant sphere. If you sketch, imagine a sphere around the radiator with the radius lambda by 6, then it is called radiant sphere. 8. The power flowing away from the source in the medium is solely due to radiation fields. The other two types of fields do not contribute to the outward flow of power in any way. It has been mentioned that only radial power component contributes to outward power flow. Other power components, theta component or phi component, they simply circulate around the radiator. The induction term contributes to energy that is stored in the field during 1/4 of a cycle and returned to the circuit during the next. Another observation, the total power radiated is proportional to square of the length of the dipole in wavelengths, implying that it is proportional to square of the frequency. And the ratio of far field components E theta to H phi is equal to eta, a clear indication that radiation is a TEM wave. Only TEM wave, it obeys, it supports the relation E to H ratio equal to eta. E theta to H phi equal to eta means the radiation is TEM wave. 11. Its radiation pattern is a circle in the horizontal plane and a dumbbell in the vertical plane. Circle means this. So in a horizontal plane, this is radiator. If you consider a horizontal plane, the pattern is circle. Radiation is equally good in all directions. Whereas in vertical plane, it is dumbbell. Dumbbell means like this. Or clearly, it is like this. Well, the radiation electric field is entirely in theta direction. Notice the term radiation electric field or the electric field part which radiates. Other terms are also there. As far as electric field of the radiator or dipole is concerned, other parts are also there, which vary inversely with the distance square and distance cube. Here we are not considering them. What we are considering is the part which is varying inversely with the distance. That part is called radiation field. It is 60 pi Im dl sin theta by r lambda. And note that expression here given is valid only when the dipole is located along the z-axis. If you recollect, all the derivation is done by placing the dipole along z-axis. So the expressions that are arrived at during the analysis, they are valid only when dipole is along z-axis. When the dipole is lying either along x-axis or y-axis, then radiation electric field acquires both theta and phi components. So what is radiation field when dipole is over x-axis? It is 60 pi Im dl square root of 1 minus sin square theta cos square phi by r lambda. This is 13th observation. 14th observation is when the dipole is over y-axis or along y-axis at the origin, then E becomes equal to 60 pi Im dl square root of 1 minus sin square theta sin square phi by r lambda. After observation, now we consider some important features of the elementary dipole. Radiation intensity. Radiation intensity is denoted by U. As we are in spherical coordinate system, U varies with the coordinates r theta phi, but we know pretty well that radiation intensity is independent of distance. It depends only on direction. Direction is denoted by theta and phi of spherical coordinates. So radiation intensity, how to find radiation intensity? Process is first compute density, radiation density. It is E square by 2 eta. E is available with us. Substitute expression for E, then we get S. From S, U. R square S is U. A little bit of manipulation gives us radiation intensity U as eta by 2 omega Im dl sin theta by 4 pi rc whole square watts per steradian. Similarly, radiation resistance can be computed. How? First we compute total power radiated. It is closed surface integral over density. Radiation density S, SDA. S is available, already we have calculated. Substitution and a little bit of manipulation gives us I square RMS 80 pi square dl by lambda whole square. From this, R radiation can be found as 80 pi square dl by lambda whole square. Then directivity. Directivity is 4 pi U max by PT. In the previous slide, we have computed PT, we have U. From U, U max can be computed. Substitution gives us D as 1.5. In log, units, it becomes 1.76 dBi. Then beam area. Definition is omega A is equal to integral 0 to 2 pi 0 to pi by 2 u normalize theta phi sin theta d theta d phi. U is available, un can be computed. It turns out to be sine square theta. Substituting un in this expression, one can get it as 4 pi by 1.5 steradian. Without doing all these calculations also, one can find beam area. How? Directivity and beam area, this product is always 4 pi. So gamma A is equal to, omega A is equal to 4 pi by D. D is 1.5, we have already known. So one can avoid all these calculations and directly write down the value of beam area. Effective length. Definition of effective length is 1 over I max integral minus L by 2 plus L by 2 Iz dz. But current over the radiator is uniform equal to Im. So substitution and performing integration gives us L effective as dl. It means physical length and effective length both are same, equal as far as elementary dipole is concerned. Then effective area. Effective area can be calculated using the fundamental relation AE is equal to lambda square by 4 pi into D. D is known to us, it is 1.5. Simple substitution gives us AE as 1.5 lambda square by 4 pi. Half power beamwidth. In case of elementary dipole, the pattern, this is dipole, pattern varies as sine theta, therefore its shape in vertical plane is dumbbell. It is like this in a vertical plane. Infinity, and therefore its shape in vertical plane is a dumbbell, and it is maximum at theta is 90 degrees and its value is 0.707 times maximum at theta is 45 degrees. As the 3 dB beam width is by definition equal to twice the angular separation between maximum point and 3 dB point, it is 90 degrees. Half power beam width is 90 degrees for a short dipole. In the horizontal plane, it is omnidirectional. The beam width becomes irrelevant. The dumbbell shape is shown here. With this, we come to an end to this session. In this session, elementary dipole is introduced. It is defined. Its fields are calculated, computed. A few important and serious observations are made regarding its functioning, and at the end some important performance indicators of this radiator are computed. Hope this session is useful to you. We meet again in another session with a new topic later.